So far, we've only talked about examples that had one electron in the d orbital. So now I'd like to shift our focus to examples of metal ions that actually have more than one electron or more than three electrons specifically. Um, I mean, if we have one or two or three even, we know that no matter what the energy difference is for our crystal field splitting energy, we're going to have three electrons populating our bottom lowest energy d orbitals. But once we hit that fourth electron, a question arises. Where do you put it? Do you put it in the lower energy level here and pair it up with the first electron placed? Or is it placed at the higher energy level, first populating all of our d orbitals with one electron before starting to pair them up? And so any electron configuration with a metal ion that has more than three of these electrons is going to have a question of where to put these electrons, and it'll depend on the size of that crystal field splitting energy. So if the crystal field splitting energy is very large, then we're going to pair it up here right away in the bottom level. And if instead we have a smaller crystal field splitting energy, we're going to place it up on the top because it won't be a huge energetic cost to populate that orbital with a electron before we pair it up at a lower energy level. When we pair up our electrons, when we spin pair them, we're putting two electrons in the same orbital. And because of that, they'll constantly be repelling one another within the orbital, which generally increases its energy, or it's less energetically favorable, might be the way to say it. However, that might be more favorable than putting the energy into populating that electron up high in a higher energy level. And so we're going to talk about these differences between large and small crystal field splitting in terms of how electrons populate within the d orbitals. And we're going to use the phrases or the terms high spin and low spin to refer to those two possible placements. So if we place it here in the lower one, this would be a low spin complex. And here in the upper one, it would be a high spin. And again, this really only becomes an issue once we have more than three electrons. So this is going to, and less than 8. So this is only going to affect our complexes that have 4 through 7 of these electrons in the d orbitals. All right, so let's take a look at a strong field ligand. So for the 4 through 6 electrons, if we have a very large energy difference between these d electron or these d orbitals, we're going to populate those electrons in the lower level, and we'll pair them up first. And that means, so for electrons 4, 5, and 6, they'll pair up, and we'll have a complex that doesn't have any unpaired electrons. And when we don't have an unpaired electron, we call it diamagnetic. And so for this case, we have a low spin complex that's diamagnetic. We have no unpaired electrons. And we're looking here at an iron +2 ion. So let's look at that same ion, iron +2, but now let's put it with a weak field ligand. Let's put it surrounded by water. Now we have a small splitting energy. And so we can actually now fill all of our d orbitals with one electron before pairing them up. And when we do that, our 4th through 6th electron now become 1 or 4, 5, and 6. And only one of those 3 electrons is going to actually pair up. And so we're now going to have a total of 4 unpaired electrons. And that those unpaired electrons are going to be paramagnetic. And this is for our high spin complex because we're populating those higher energy levels before we pair up our electrons. So let's look at an example of cobalt with fluorine. So if I wanted to tackle what I would expect for this, is it high spin, low spin? Is it going to be paramagnetic or diamagnetic? Like, how's it going to interact with a magnet? I would start by saying, okay, I've got cobalt +3. And even though I'm expecting a larger gap from that cobalt +3 with that larger magnitude of charge, I need to check in with my ligand. And that's going to be fluorine. And so looking for fluorine, I'm finding it here in my relative ligand field strengths. And so this is a weak field ligand paired with a high magnitude charge metal ion. And so honestly, it could go either way in that sense. And so a lot of this being precise in this regard or exact is going to come from actually doing an experiment to determine what's going on. For this class, I think we should focus not on the metal charge, but rather on the comparison between the different crystal fields ligand strengths, as I think that's kind of appropriate for the level we're at. And so let's focus and prioritize that fluorine. That fluorine's a weak field ligand, so let's say that our crystal field splitting will be smaller, despite the magnitude of charge coming from that cobalt. So it's an octahedral complex. I have those 6 fluorine around it. And so my crystal field splitting pattern will be 3 lower and 2 higher. And I'm going to add in my 6 electrons. Cobalt +3 has 6 D electrons. And I'm going to fill each one up halfway first. So 1, 2, 3, 4, 5 before I pair. And I'll only have one set of paired electrons. I'll have 4 unpaired electrons, and I'm going to have a diamagnetic compound. I'm sorry, paramagnetic compound. All right, so now what about nickel cyanide? I'm going to take a quick pause for just a second. Pause the video. Try it out on your own first. All right, hopefully that worked. So looking at my nickel cyanide, when I look at my crystal field here, I'm seeing that my cyanide is really far on the strong field ligand. I also do have a nickel that is a +3 ion, so that kind of supports a larger difference between my energy levels and a larger crystal field splitting. So when I draw out my orbital diagram for my d electrons only, I'm going to populate my electrons here with a large crystal field splitting energy. And so that means I'm going to pair up my electrons first. So nickel +3 is a D7 electron configuration. And so I'm going to start by populating 1, 2, 3 electrons. And now I'm going to pair them up because I have a large gap, 4, 5, 6. And then I come in with my 7th at the top when there's no more space at my lower energy levels. So I'll have a paramagnetic compound again with 1 unpaired electron. So before we had 4 unpaired. Now we have 1 unpaired. And the nickel case was a low spin complex, whereas our cobalt example was a high spin complex. Give these problems a try on your own, and I'll do the solutions in the next video.